Hi, I'm Jeff Berryman, and I would like to thank everyone on the interview committee for allowing me to interview via video. Today we're going to be talking about the input and outputs of a PLC. The PLC specifically we'll be dealing with is the Allen Bradley. The input-output modules on the Allen Bradley, which I will be demonstrating later, is the 1769 IQ32 for the input and the 1769 OB16P for the output modules. The first section we will talk about is the analog input section for the Allen Bradley 1769 IQ32 module. This input section, of course, contains connections to the outside world, a resistor, a capacitor, an optocoupler, and the output to the microcontroller. The optocoupler is used for isolation from the real-world devices to the bus contained inside of the PLC microprocessor. Due to the way the input is configured with a resistor and a capacitor, it will limit the speed of a signal that can be detected by the device. According to Allen Bradley specifications, the minimum rise time is approximately 8 milliseconds. Also, when the LEDs inside the optocoupler are biased on, it causes a current to flow through the resistor. Since they have back-to-back LEDs, the current can flow either way. You can have this input to be positive and negative, or you can have this input to be negative or positive. Allen Bradley does this to allow the module to sync and source at the same time. In syncing inputs, you have connections to the PLC, and you have a ground, or as they call it, a DC common. And I'll just call this input 1 and input 2. And for this particular situation, if I was to place a switch here, I am taking the terminal to ground, which means I'm syncing the input. Conversely, if I have another input set up, also have, and I should have drawn this over here as well, plus voltage I'll place a switch here. I'll pick up the same input 2. Here I'm sourcing the input, which means I'm applying a voltage to terminal, I2. In both instances with Allen Bradleys, you have to have an external power supply between these 2 points. Typically 24 volts DC. Since a minimum amount of current is required for the input to turn on, this tends to abate the noise that may be present in lines and wires running through machines. Next, we'll talk about the output module in the Allen Bradley, specifically the 1769 OB16P. The P at the end of the module indicates that it's protected. So let's talk about what the output looks like. From the PLC itself, which sets an optocoupler with the LED. And on the output side, I will draw outside of the box. However, it is coupled with light to it. There's a voltage regulator, which goes to a plus DC bus, addition, a minus DC bus. After this, the output method they choose to use is a FET style output. And here, as the light turns on from the LED, this biases the junction of the FET on. And this is the basic way the output is configured. Also, inside the output, they have a few Zener diodes. The Zener diodes are to protect from reverse power conditions. And the Zener diode here prevents the output from being reversed and protects the module in that manner. Each of these Zeners, I believe, is about 39 volts. So let's talk about why they use FET rather than a transistor on the output. Typically, transistors, when set up as a source, which would be this manner, which is going to be the output. I'll use an NPN. So since the transistor is sourcing the voltage out, this NPN, this is technically called an emitter follower. And at this point, it requires a voltage that is 0.6 of a volt higher than the emitter. Typically, you cannot source as much voltage out as you're putting into the device because of the limitation across the base emitter junction. Also, the transistor is limited internally by its beta, or its DC gain. A FET, on the other hand, is a voltage-operated device. Technically, it is a voltage-controlled current source. In this case, the current can still be limited on the output of a FET. However, it takes a voltage to turn it on, which means you negate the fact that it requires current through a junction to make it work. This allows it to be a little bit faster and a little bit cleaner output. Also, the FET's turn-on resistance can be quite a bit lower than a transistor. This is important for power dissipation, so it allows higher power to be sourced from the output module that has a FET versus the output module that has a transistor that would have the same size heatsink. I will now talk about syncing and sourcing outputs, a general overview, not specific to the Allen Bradley. Typically, when you source something, you have a positive voltage or a higher potential voltage that will drive through, let's say, a switch, and we'll go to a light bulb. In this particular instance, the light bulb is going to ground. When I push the button in, the current will flow. We'll do conventional, from the positive to the negative through the bulb and make the bulb light. I am sourcing potential to the bulb. By swapping the position of the switch in the bulb, I'm now turning this into a syncing circuit. This means that I sync the bulb to ground. There are several situations where it doesn't matter which way you put these. For instance, if these were dry contacts, as I have drawn here, just simply a switch, the switch can be placed anywhere in the series line and it doesn't matter. However, for an instance like this, if I use my control point to be a transistor, I'm just going to say bias. So at this point, what has to happen is I have to apply a bias current to the transistor. And remember, it takes 0.6 of a volt between these 2 points to turn it on. So let's say this is 12 volts. So if I put 12 volts into this, I would have out here about 11.4 volts. So it would turn the light on. However, we're limited because we have 12 volts here, and this is all the voltage we have available. But if I were to swap the configuration as it is above, and use this as a sinking output, now it only takes 0.6 of a volt to turn this junction on and allows nearly the full 12 volts to be present at the bulb. In this situation, only 0.6 of a volt is required to turn it on, where in this situation it requires at least the source voltage, and you still don't quite get the output voltage as you should. It's close enough in most situations, but typically not. So in this situation, when you see relays being driven on outputs, particularly of PLCs, and they're driven with a transistor, they're typically in sinking configuration, and you also have protection diode that sits on the output of it to protect against back EMF when the coil is released. Here you can see the Mechatronics trainer that I will be using for the remainder of this demo. The Mechatronics trainer is made by Amatrol and contains 7 modules, including a robot module. We'll first begin by applying the power to the PLC and the trainer, which I already have, and connecting the communications to the computer. In this instance, it will be a 10100 Ethernet connection. Next, we must verify that the communications is working. In this instance, we will go to Rockwell Software and we'll go to RS Links Classic. Once Classic loads, we'll then go to the Ethernet port and allow it to poll. You can see that an X appeared over top of this one, which indicates that it is not connected to the system, but this one is. So we'll select this one, minimize the box. Now we will go to RS Logix 5000. The quick start page appears. In this instance, I can go up to communications, who active, the Ethernet port. Once again, allow it to poll. Select the one we have, select the backplane, select the processor, go online. We are now online, and we can draw up the main routine that is in this particular PLC. you can see on this particular one, it's flashing green because of a timer that is firing. This one is solid. Obviously it is a not input, it has the line going through it, or normally closed, as they would call it, or examine if closed in Allen-Bradley. And in this program you can see outputs, which are typically on the right hand side of the rung, and your inputs on the left hand side of the rung. If you wanted to, we can create a new project, and you can see the controller is a 1769-L32E, which is the correct controller, and it requires a controller name, and I'm just going to call this one Test. And this will bring up a new plane in which we can start our new programming if we so desire. Before you can begin programming in the Allen-Bradleys, you must configure the inputs and output modules. So you have to go to I/O configuration, compact bus local, create a new module. In this case, there will be digital modules on this one, and I have to select the proper module. If you do not select the proper module in the proper order, it will not work. The first module in the back plane is an input. It has a 1769 IQ32. And you can check in the microcontroller always, and it will state on the door what the module is. Say OK. In this instance, you do not have to give it a name, and just for time's sake, I will not. And I need to select the output module. And in this case, it was an OB16P with the protected outputs. And once again, I'll not select a name. Now I have my inputs and output modules listed on the bus. I can go to the main program, to the main routine, and it starts up with a blank slate. If I choose, I can add an input, and I'll do the examine on, and I could put an output in as well. Let's configure the input first. I'll go ahead and put the output in. Now, there's a question mark over top of both of these because it doesn't know which one you want to do. So if you double click, go down, and you'll see one called local1.I input. Go to the data field, select the drop down arrow, and I'll select number 2, just in this case. And now I've chosen an input, which will be the number 2 input on the input module. And for the output, same thing, double click. In this case, it's local 2.O for the output module, data, and I'll use output 1 in this case. And that's it. You have a simple, very simple one-rung program. And if I chose to, I could place this program into the PLC, and the PLC would run this particular program, which is very simple. I will now walk through and give you a quick overview of everything in our mechatronics lab. All of these were built in-house as projects for students. This is our most complex one. It is a part sorting machine. It sorts parts or cubes that have one shiny side into a particular staging area. There's also cubes that have no shiny sides and cubes that have multiple shiny sides. We have rotating clamps to allow the cues to be rotated into the proper position. The one manufactured item we have in our lab is the Mechatronics strainer from Amatrol. This particular one builds spool valves and uses a FANUC robot. We also have several Mitsubishi robot arms, another single FANUC 200 ID. We have a couple of conveyor trainers and some PLC trainers as well. And this is a stepper motor trainer. And in our lower mechatronics lab, we have many types of PLC trainers using Automation Direct DL05s and CLIC. The students begin on the AB Micrologics. We also have a few more Amatrol trainers. And we have the Amatrol mechanical drive systems benches as well, and pneumatic trainers, and we also have hydraulic trainers, which presently are at main campus. A lab trainer that I recently constructed uses a temperature probe and a heater made out of light bulbs driven by a DC drive. This is then driven by a PLC, CLIC PLC analog output and input modules. And the student is required to control the temperature of the probe. I found that not many people get good experience with analog systems, even though they're still used widely in industry. I've constructed 2 of these trainers so far, and this is something that the students actually do in the ELC 228 class. Once again, I would like to thank the committee for allowing me to present my teaching demonstration in this online format. I look forward to hearing from you.